For this last video in this little tute series, let's re-implement ensemble nets. So this is an idea I've been playing around with for a little while. It came about from this idea I had, which was basically that so far the way we've been doing things is to use pmap to represent a single model that gets shipped to all devices and that operate on multiple data. But I was just curious about the idea about what if we did it the other way around, and instead of parallelizing over the data, we parallelized over models. So what if we use this pmap structure to say, let's run multiple models over the same data? And that's exactly what an ensemble is. So we can use these structures like pmap and vmap to build ensembles as a single unit. So I've got a series of blog posts about this. I won't go into too much detail. Just to re-implement them, please read the blog post if you're interested. That's cool. So most of this is going to be sort of stuff we've seen before. We're not going to use tpus for this one, but we will have this idea of the 8 devices. We need haiku and optax again, so this is what we're going to be using again to define our simple model. These were a couple of little helper functions we had from last time. You remember we had this idea of sharding, which is when we sort of distribute our data over multiple devices. And a little helper that I'm going to use here to sort of describe the shapes of elements in a pie tree, just as a way of sort of doing some debugging. So we're going to have some pie trees that are starting to get a little bit more complicated, you know, multiple models, and each model having multiple layers and stuff. And when we print them out, rather than printing out everything, I'm just going to print out the shapes of things and their types. It's just a little bit of an easier way to sort of do some reasoning about things. As before, we're going to have a simple, very simple linear model. So I've got some x's over a range, and I've got the y's I'm making. And remember, again, we're a bit more explicit about the shapes of things here to support haiku. So this is a 1D problem. Both x and y are one-dimensional. Same model as before, very simple linear model. Now, we're going to do 2 versions in this collab that sort of follow along the sort of thought process I had when I was playing with ensemble nets first. We're going to start first with this idea about an ensemble net of 8 models. So this is interesting because let's go through what we did last time with the way that we built models using haiku. So you remember haiku has this idea of doing a transform, and then from the transform we can initialize. What we're going to do this time though is not just initialize 1 model, we're going to initialize 8 models, and we can do that with pmap. So we've got the initialize function, which haiku provides for us. Usually we are only calling this once to get 1 model. What we're going to do in this case is to build 8 random keys and actually initialize across those 8. So what we get here is this params now represents not 1 model, but it represents 8 models. And this is very similar to what we had before, where the data didn't represent 1 instance, it represents a batch of instances. Now we've got params representing not a single model, but a batch of models, so to speak. And so all these sort of structures we had are the same. It's just that we're now going to be doing the parallelization over models instead of data. So now this params represents 8 models, and you can see how with this pmap and the initialization, it's already sharded. So we've got this symbolic thing, params, which represents 8 different models on the 8 different devices. Cool. So if we I think that params, so a particular param we can see here, just to use that shape sub to give a sense of things. This is that little debugging. We've got, it represents a linear model, which has B's and W's, but there's actually 8 of each. So, this idea that we've got the 8 models. Cool, and what we can do is we can just really simply plot them, I guess. So here's the 8 models, and, we randomly initialize them, so they're sort of all over the place, as you'd expect. Now, if we've got this now thing that represents 8 models, how do we do inference on an ensemble? It's pretty straightforward. We just basically run all the models in parallel, and we can do that in parallel in a couple of ways. Here I've just used vmap. So we've got an apply function that haiku gave us. We can transform that apply function to work in a vectorized form, just like we did with everything else. So I've now got this version of the model that actually expects a vectorized form of the parameters. And so we can call that with our parameters because the parameters are representing 8 models. And we get this predictions back. Now the predictions have a dimension which corresponds to the size. So this was the X basically. We've got 128 examples. But now the predictions have this extra leading dimension, which represents the 8 different models. And with an ensemble, what do you do? Well, for an ensemble like this regression, we can just average them. So we can literally just take the mean of those predictions on the first axis, and now we get the average. And this is what the ensemble is predicting. So this, I've just got one picture I want to show from the blog post, which is that idea where, we've got a single image, they're being run on multiple models. In this case, we were doing classification. And there's some way of combining those outputs. In this case, with logits, we can just sum them, but in the regression case, we just sort of take an average. So this is the representation of how we do inference for the models. Cool, so very, very, very simple, very straightforward. Training though, training's a little bit different because usually with an ensemble, what we've done is we've trained multiple models sort of independently, and then we've sort of combined them later. How are we going to do this training if we've got this thing that is representative of a single model? And the first thing I tried with this, it has an interesting failure mode, which sort of in hindsight totally makes sense, but I didn't pick it at the start, which is if we train things jointly, what do we sort of get? Let's go through it. So what do we need to do if we're going to be training these 8 models in sort of lockstep? We need to have 8 optimizers. So we can use, again, this idea that we did as before to actually build an optimizer with optax. Now remember that optimizer gives us an initialization function, and before we were only calling that once. But now our params represent 8 models. So we can p-map over that initializer to get a version of the optimizer states, which is again representing 8 models, not just one. And it's in exactly the same structure. So it's a pie tree, and where the leaves have this extra leading dimension of 8. So now we've got this symbolic representation of the optimizer states that represents all the optimizers on all the devices. Just like before, we can run pmap to train this thing. So this is basically the same loop we had before, but you can see now what's interesting is when we were doing the update function, this is pretty much the same update function we had before. We had, the gradients, and we had the optimizer update and everything. The way that we're doing the parallelization, we've changed here now what we're doing in terms of what things are being parallelized over. Before, we were not parallelizing over the parameters or optimizer state, if we were just wanting to broadcast them. So in the first version, in the last one we had, we were saying none for the parameters and optimizer state. This was sort of, that's the version where we were shipping things out, where we had just basically one model, but we were parameterizing over X and Y. Now we've done, as this first example, we've done the opposite. We're actually saying, don't do any parallelization of X and Y. So send all the devices, all the data, the X and Y pairs, but do the parallelization over the parameters optimizer states. So each device is now acting on its own model. And these are models where we're not, we didn't replicate this model. These are 8 different models. This leading dimension in the parameters and optimizer state isn't a copy of the one model, it's 8 different ones. So this runs, and one thing that is, we're going to make sure we see here is that there is this idea that we're doing the ensembling of the devices across the devices. So this is sort of, parallel with what we had before. We do a prediction that gives us actually, remember, eight predictions. So we do an average over all the devices. So each device is doing sort of an average of how it's sort of contributing to the ensemble. And then we do the optimizer update. So each of the models is being trained independently, but they're being trained because of this p-mean here to only behave as if they're acting together in one big go. And what that has this interesting effect was, and this is something I'll talk more about in the blog post, we're not really doing an ensemble here. All we're doing is 8 models that are running independently, but through this big bottleneck, this p-mean here, they're only ever being trained to work together. So really, it's just really one big model. It's effectively one big model that has this bizarre bottleneck where we run them all and then we just basically average the predictions. Backprop doesn't care about your structure. It's going to care about the fact that this is one big model effectively. It's just a strangely parameterized model. So what we get is we get something that looks okay, but if we actually look at the results might be okay, but each individual model isn't good by itself. And that's really because they're only ever trained to work together. So each individual model sort of might have this, little quirks where one goes too high, but as long as some of them go too low, they sort of average out, literally average out. So there's no motivation, the way we've structured things here, to make any individual of those 8 models be good by itself, because they've only ever been trained in a lot of 8. So that's cool. So what I wanted to do next, a little bit to play with then, is like, how do we stop this? And when I first saw this, I thought, well, this is a little bit like dropout. It's a little bit how we have the sort of idea that nodes often in a layer will overfit too much to the idea that they're sort of co-located. So the solution in that case, this is interesting idea, dropout, where we sort of half the time when we're doing a training step, we literally drop half the nodes out, because that sort of removes the ability for any node to be dependent on anyone else because they're not there half the time. We can do the same thing with this, but we can do it at the model level. So while we're doing this training, we'll actually train in a forward pass different combinations of the models. And if there's different combinations of the models can't sort of specialize too much. They can only sort of, they can't be sort of dependent on a whole group together because they don't really know who their group's going to be. So each individual model has to be a little bit more robust to that. So there's a couple of different ways we can do this. And this is an interesting sort of, I'm still not exactly clear what the best way to do this is, but I'll go through the example that I've sort of landed on so far, and I'll play around with it a little bit more. If we're going to be doing a dropout of say 50%, then what we're going to actually be training in some ways is we're going to be training on 16 models. And each time you sort of run a forward pass, we actually only want to use 8 of them. Because that's the PMAP, the number of devices we're dealing with is 8. So if we think about that from that sense of like wanting to run 8 models, how are we going to select the 16 models? So there's a couple of different ways this could go, two sort of extremes. One is that, on the host, we could have our 16 models, and then when each of these, we'll sort of decide which 8 and then sort of ship all the parameters to the device basically differently every time. That's one extreme. Another extreme could be to have all 16 models replicated on all devices. So all devices have all 16 models, and then sort of we decide which ones as we go along. But the way I've sort of landed on things, which is an in-between, I think, is to have each device, each of the 8 devices, have 2 models, or, in general, it could be 2 or 3 or 4 or whatever. And what we do during the forward pass is we decide, basically, for each device, which of its 2 is it going to use. So we've got 8 devices, each of them has 2 models. For this device, let's use the first one. For the next device, let's use the second one. For the third device, let's use the first one. We'll do this randomly. This doesn't give us the ability to, for every forward pass, have an arbitrary random combination. All it's really doing is saying across the 8, we're sort of going to pick which of the 2. So it's a sort of in between. So it's not perfect, but it means that we can have this minimal amount actually on the devices. And all we need to do during this sort of forward pass is to send the data and to send this minimal sort of, basically, I call this a dropout key, which is a bit of a mask to say, which device should use which of its 2 models. So, maybe looking at the code will make that a little bit clearer. So we're going to start with, no matter what, if we're going to be doing this 50% dropout, we need to have 16 models instead of 8 now. So let's rebuild this whole thing, but with 16. So now we've got a model set that represents 16. Let's do the same with the optimizers. So we're going to, this is like before, we're just, again, we're rebuilding our optimizers, but with 16 of them. Now, if we're going to have this idea of 8 devices and 2 models per device and 2 optimizer states per device, actually, all we really need to do is just to reshape that leading axis of all these things to go from 16 to 8 by 2. So instead of here being B being 16 by 1, we're just going to say it's now 8 by 2. And the next one is instead of being 16 by 1, it's now 8 by 2 by 1. So the 8, again, is the PMAP, the number of devices. This is we're going to shard over this first axis. Each device is going to have 2 models, and really the forward pass for training will be about which of the 2 do you pick per device. Cool. So we can do like we did before. We can shard both the parameters and optimizer states. This is basically this little helper we had that's basically PMApping them out to the devices. And let's just plot them really quickly to see what they look like. It's again the 16 random models, and if we just pick W, for example, as a parameter, it's all over the place. This is exactly what we wanted. Now the update is going to be like before, but it's a little bit tricky now. It's a little bit more. This is probably the biggest update function we've had, because now if we start from the training loop, let's go all the way down to the bottom. What we're going to be doing actually during the update step, before we were only updating the parameters, we're only passing parameters, optimizer state, and the X and Y. What we're going to do now is this little extra bit where we're going to generate per step what I call this dropout key. So what are the indexes of the submodels we want to play with? So we're literally going to be generating just basically it's a shape 8 devices basically. So it's an 8 long, and the values are just 0, 1. So 0, 1, 1, 1, 0, whatever. And what we do, this is a very, very minimal amount of information to generate on the host. And we're just going to ship that out to all the devices. And because we're going to be parallelizing over it, we're going to be parallelizing here over this in axis. Each of the 8 devices is just going to get one of those 0s or 1s, basically. So the first one might get a 0, the next one might get a 1. If we look up here, what we've had to do, the best way to frame this, I'm still not 100%, and this might be a bit clumsy, this code, but so each of the, during the PMAP on each of the devices, each one's getting this little index here. And what we're going to be basically doing is at the start, we're going to be slicing out the parameter and optimizer state for that index. And we just do that here with this little a little tree map. So we're going to be tree mapping over each of the parameters and just saying basically just grab that one, because you remember that the parameters up here are like, if we look at this one, they say this one, the B here, it's 8 by 2 by 1. The P map's going to strip the 8. So now this parameter is going to be 2 by 1. And we just wanted to pick one of those, either the 0 or 1. And so here we're going to basically, that slices them out. This puts these sub parameters and sub optimizer state in the right form for what the rest of the code expects, like the loss, etc. So we step through, we calculate the losses, we do the update with the gradient and all that sort of stuff. And then we've now got a new version of the parameters and optimizer state. We just have to put them back into that sort of, nested structure. So to do the reverse of this, basically, we slice them out. We need to put them back in. And we just do that here with a bit of code, which is basically the opposite. We everything's immutable in JAX, so we can't do the direct assignment. We have to use this little thing, index update. So this is equivalent to setting the index, the value with this new value. So this is basically the reverse of that first part. What this is now doing is it's basically training only that one model. And because everything up here was to do with that sum over the device, over all 8 devices, this mean, when we're doing the averaging during the sort of the loss calculation, it's going to be different. It's going to be a different combo of models every time. Now it's not a perfect, again, because this idea that we're only just picking the 0s and 1s, it's not going to be a perfect mix every time, but it's not like a perfect 50% sampling of models, but it's pretty good. And in fact, this idea that we've had 2 submodels per device, we could make that bigger. We can make it like 4, for example. So we could say each device has 4 models on it rather than just 2. And we just pick a random one of those 4 models, 0, 1, 2, or 3. So that would give us even more coverage to make things more random if we wanted to increase the number of models. That sort of works. And as we'd expect, we get a little bit more of a robust example where I didn't train this for very long, and it's just interesting to see the dynamics of this, but we get a much better spread of models, and these will eventually sort of converge down. And we get what we sort of expected in terms of a bigger, a tighter range around the true values. And in fact, this idea of the variance of these sort of results in terms of the sort of prediction values here, in the classic ensembling sense, actually gives us a sense of confidence. And that's something that we talk more about in the blog post. The idea we can actually use the range of the ensembled values that are coming out of prediction to give a sense of where the confusion is, because in the blog post for particular classes that are confused, we see the ensemble giving a wider range of predictions, which is one of the good things we actually want out of ensemble. Cool. So that was sort of the final part. There's one little small part. We're going to add another little tune at the end. It's just a bit of closure on things, but generally that's the idea. We've re-implemented ensemble nets using Haiku and Optax on TPU across multiple devices, using first a device parallel, a sort of data parallel, but now this model parallel to implement ensemble nets. So one more video and then we're all done. So thank you.